In this section, we're going to talk about mutually exclusive and overlapping events. Two events are mutually exclusive events if they cannot both occur in the same trial of an experiment. For example, if you flip a coin, it could land heads up or it could land tails up, but not both at the same time. So in order to get both results, you'd have to do multiple experiments, or in this case, multiple flips. Another example is if I take a 12-sided die and I roll it, a few different things could happen, but I want to know what's the probability that the result is even or a 7. Well, let's draw a diagram and label some events. Let's let event A be the event that you roll an even number. So there are 6 even numbers that I could get: 2, 4, 6, 8, 10, or 12. Event B is rolling a 7. Well, there's only one 7, so I've got that there by itself. None of this overlaps, so between A and B, I've got nothing in the middle here in my Venn diagram. And then the numbers 1, 3, 5, 9, and 11 are on the outside because they are neither even nor are they a 7. So let's answer the following. Calculate what the probability of event A is. Well, event A is rolling an even number. Since there are 6 even numbers out of 12 possible sides, this would be 6 over 12. We could reduce this to 1/2. So half the time you roll this 12-sided die, you will get an even number. What about the probability that event B occurs? Well, event B is getting a 7. There's only one 7 out of the 12 sides, so this is 1 over 12. Now, what about A or B? A or B means that either one of these things could happen. Either I could get an even or a 7. So this would be 6 plus the 1 over 12 sides. Well, this is 7 over 12. And now I've got to calculate the probability of event A plus the probability of event B. Well, the probability of event A is 6 over 12. There are 6 even numbers. Plus the probability of event B is 1 over 12. There's 1 7, which is 7 over 12. This shows for mutually exclusive events, the probability of A or B as one event is equal to adding the probabilities of event A plus the probability of event B. But that's for mutually exclusive events. What if I look at overlapping events? These are also called inclusive events. These might have one or more outcomes that they have in common. Let's go back to a 12-sided die again. This time we're going to roll it and ask, what is the probability that the result is even or a number greater than 7? So let's let event A be the event that you roll an even number. Here we've got 2, 4, 6, 8, 10, 12. And event B is going to be the event that I roll a number greater than 7. So that's 8, 9, 10, 11, and 12. When I draw this diagram, I notice that event A and event B have some overlap. The results 8, 10, and 12 are both even and greater than 7. So I've got 2, 4, and 6 that are the only 3 numbers that are even and not greater than 7, so they're by themselves. I've got 9 and 11, which are greater than 7, but not even, so they are by themselves. 8, 10, and 12 are both even and greater than 7, so there's overlap there. And then the numbers 1, 3, 5, and 7 don't belong under either of these categories. So let's calculate these and then try to see if there's any difference between exclusive and inclusive or overlapping events. The probability of event A. This is the probability that I get an even number. There are 1, 2, 3, 4, 5, 6 even numbers out of the 12. So this will be 6 over 12, and I can reduce that to 1/2. All right, now the probability of event B. This is how many numbers are greater than 7 out of these 12. So I've got 1, 2, 3, 4, 5 numbers. They are 8, 9, 10, 11, and 12. So the probability that a number greater than 7 is rolled is 5 over 12. What about A and B? A and B means that both of these things have to happen. That means that a number must be even and it must be greater than 7. There are 3 results there, 8, 10, and 12. So this is 3 over 12. And I could reduce that to 1/4. Okay, what about A or B? A or B means one or the other. So all of these results here that are in the shaded area are 1, 2, 3, 4, 5, 6, 7, 8. This is going to be 8 out of 12. And I can reduce this to 2/3. But what you'll notice is with mutually exclusive events, that was the last one, the probability of A plus the probability of B was equal to the probability of A or B. However, with inclusive or overlapping events, that's not the case here. In this case, I've got 6 over 12 for A, I've got 5 over 12 for B. If I were to add those together, it would be 11 over 12, which is not the same as what I've got here, 8 over 12 or 2/3. So instead, let's calculate this. What's the probability of A plus the probability of B minus the probability of A and B? So the probability of A is 6 over 12 plus the probability of B is 5 over 12 minus the probability of A and B is 3 over 12 This is equal to, let's see, 6 plus 5 is 11 minus 3 is 8. This is 8 over 12, which is going to reduce to 2/3. Here I see for all events, the probability of A or B is equal to the probability of A plus the probability of B minus their intersection, the probability of A and B. This works for both inclusive and exclusive events. So if I go back to the last result, here I said I could just do the probability of A plus the probability of B. Well, really, if I do the probability of A plus the probability of B minus the intersection, it will also get me the probability of A or B. Because this would be 6 over 12 plus 1 over 12, and then minus 0, because there's no overlap. So this formula here actually works for all of my problems, whether these are mutually exclusive or they are overlapping. So we're going to use this. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of their intersection, A and B. This is actually called the addition rule. And we can also use this with data, with tables. Let's take a look here. Let's say that I've got a school, a high school, with 9 through 12. So I've got freshmen, sophomores, juniors, and seniors. And within this school, there are 808 students in total. So how I read this table is for freshmen, I've got 98 boys that are freshmen, 102 girls that are freshmen. There are 200 ninth graders in total. For sophomores, I've got 104 that are boys, 106 that are girls, so there are 210 10th graders. For juniors, I've got 100 boys and 96 girls. That's 196 juniors in total. And for seniors, 94 and 108 boys and girls, respectively. So that's 202 in total. Another way to look at this table is go the other way. There are 98 freshmen that are boys, 104 sophomores that are boys, 100 boys that are juniors, and 94 seniors that are boys, for a total of 396 boys. And I could do that same thing by looking at the row for girls and see that there are 412. No matter how I look at this, if I add up all of the grades, I get 808 total. If I add up how many boys and how many girls, I also get 808 in total. So how is this useful? Let's say there's a random drawing. Any student who attends this school could receive a free ticket to prom. So they don't have to pay, whatever it costs, maybe $50 or $80, whatever a prom ticket might cost them. One person is going to receive a free ticket. So I want to know, what's the probability that this free ticket is going to go to a senior? Say all their names are put into some kind of container, and then they're shuffled up, and then one name is drawn. What's the probability that that name belongs to a senior? Well, that's going to be 202 over 808. That's because there are 202 seniors and there are 808 total students. So the probability of getting a senior is 202 over 808. What about the probability that I select a girl to obtain this ticket? So if I look at my table, there are 412 girls out of 808 students. So the probability that it will go to a girl is 412 over 808. But if I wanted to get really specific, what's the probability that a senior and girl, or in other words, a senior girl, is going to receive this ticket? Now, instead of looking at all seniors or instead of looking at all girls, I'm specifically looking at the 12th graders that are girls. There are 108 of them out of the 808. Okay, so now I want to know, what's the probability that either a senior or a girl will get this? So to do that, I'm going to do the addition rule. This says the probability of getting a senior or a girl is going to be the probability that it goes to a senior plus the probability that it goes to a girl minus the probability that it goes to a senior girl. The reason for the addition rule is because I want to eliminate the overlap. When I'm looking at how many seniors there are and how many girls there are, take a look. Seniors, I'm going this column. Girls, I'm going this row. What you'll notice is the overlap is this 108. I've counted it twice accidentally. That's why I have to subtract it once. And that's why you add these two together and then subtract where it intersects, where it overlaps. That's for accounting that you've counted them up twice. Okay, so this is going to be 202 over 808 plus 412 over 808. And let's subtract the overlap, 108 over 808. All right, now 202 plus 412 minus 108. This is 506 out of 808. Okay, or roughly, if you wanted to know, that'd be 506 divided by 808, and then times 100. There's about a 62.6% chance. So I just take the 506 divided by 800 and multiply by 100 to get a percentage. 62.6% chance that it will go to either a senior or a girl. Okay, this next one, I've got a table of flights. So this is going out of some airline. There are domestic flights, so ones that stay within the country, and there are international flights, ones that leave the country and land in another country. There are some that are going to be late, and there are some that are going to be on time. I want to know, what is the probability of domestic or late complement? What does that mean? Complement, if you recall, is what is not that. Okay, what is not domestic or late? So before I get to that, let's just take a look at the table and try to calculate a few things before we even get to this domestic or late complement. All right, there are 18 flights in total that are late. 12 of them are domestic flights, 6 of them are international flights. For on-time flights, there's 162, so quite a few compared to the 18. 108 domestic flights are on time, 54 international flights are on time, and there are 180 flights in total today. 120 of those are the domestic ones, and 60 are international. So let's say that I want to pick a random flight to give away something to all the passengers. Okay, we want to be maybe a gift to all my loyal passengers on a certain flight, but I don't want to do this for all 180 flights because that might get really expensive. As the airliner, maybe you want to do just pick one of the flights, and then everyone on that flight will get a free ticket. Okay, a free ticket to a destination of their choice within a certain range. That'd be really nice. So what is the probability that if I just took all of the flights and I, again, wrote down their flight names and I put them in a box and I shuffled it up and I pulled one flight out of there, what's the chance that it would be a domestic flight? Well, there are 120 domestic flights, and there are 180 flights in total. So the chance that I pull something that's a domestic flight would be 120 over 180. All right, what if I pull one and it's a late flight? Do they still get it? I suppose, because I said that any flight, whether it's on time or late. So what's the probability that I get a late flight? Well, there are 18 flights that are late over 180 in total. Okay, so now what's the probability that I get a flight that is domestic and late? So a domestic flight that is late on arrival. So let's take a look. Domestic flights here, late on arrival. There are 12 of them specifically. So 12 out of the 180. So now let's calculate domestic or late. Domestic or late. So that's going to be the probability that I get something domestic plus the probability that I get something that's late. So it'd be this row here, top row, and then the left column, 120 over 180 plus 18 out of 180. But then I have to subtract the overlap, the ones that are domestic and late. So I'm subtracting 12 over 180. So 120 plus 18 minus 12. This is 126 over 180. Now that's domestic or late. The true probability, what I'm actually trying to find, is the probability that I select domestic or late complement. Or in other words, something that is not domestic or late. Well, out of 180 flights, 126 are domestic or late. So if I take the amount that I have in total and I subtract that 126, then the complement of that would be 54 over 180. Okay. Now all of this could reduce, so depending on what the assignment looks like or what problem you get on a test, you might want to reduce some of these fractions as well. So 54 over 180, for example. Math, enter, enter. This would be the same as 3 over 10. So depending on what the assignment is asking you or what your test looks like, you may want to reduce your fractions. Okay, let's keep going. Got a couple more. So in this one, there's a study done on people who take medicine for headaches or not. So when you get a headache, do you take medicine for it? Do you take Tylenol or Advil or something to try and reduce the pain that you have for your headache? Or are you the type that, you don't want to take as much medication as, other people? You'd rather just kind of see if there's a way that you can naturally get rid of your headache. Maybe just drink more water, get more sleep, something like that. So there were 100 people in this survey. And of these 100 people, we asked, do you have a headache? And do you want to take medication for having a headache? So as it turned out, when we asked those 100 people, 27 of them had a headache, 73 didn't have a headache. And when we asked, do you have a headache? Do you want to take medicine? 12 of them said, sure, I'll take a Tylenol or something. Now, I'm not saying that we gave medicine to random people or anything. This is just, some random numbers I kind of pulled out. Now, 15 of them didn't take any medicine for no headache. So 73 didn't have a headache, but maybe it was a placebo effect where do you want to still take, maybe a Tylenol, just one Tylenol? 48 of them said, sure, I'll still take a Tylenol. Maybe I've also got like a backache or something too. So 48 people also still took one, even though they didn't have a headache. And 25 people passed. They said, no, I don't need anything right now. So in total, there were 60 people that took some medication, 40 that did not take any medication. So if I want to, after this survey, interview a random person who took this survey, say I've got all 100 of them still in the room, I want to pull one of them at random to just ask them a few more questions. How old are you? Did you get much sleep the night before? Why did you take medication if you did? Why didn't you take medication if you didn't, etc. So just a quick interview with one of these people or some of these people. What's the probability that I would select someone in that room who had a headache? Well, 27 people had a headache out of the 100. So that'd be 27 over 100. Okay, now what's the probability that I select someone that did not take medicine? So the probability of no medicine. 40 people did not take medicine out of 100 in total. What's the probability that I pick someone at random that had a headache and they didn't take medicine? So let's get really specific here. Headache and no medicine, there were 15 of them. So 15 out of the 100 had a headache but did not take medicine. All right, now I want to know, if I pick someone at random, what are the chances that they either had a headache or they didn't take any medicine? So this would be the addition rule. The probability that I pick someone that had a headache plus the probability that I picked someone that didn't take medicine, and I've got to subtract the overlap. So this would be 27 over 100 plus 40 over 100 minus the overlap, which is going to be 15 over 100. 27 plus 40, subtract 15. This is 52 over 100. In this last example, I'm comparing sugar candy versus sugarless candy. Okay, let's say I've got 100 children whose parents signed a waiver for this experiment, and we said we're just going to give them a piece of candy. We're not going to mention anything else. We're just going to say, here's a piece of candy. Why don't you have it? And some of them are going to get candy that has sugar in it, and some are going to get candy that is sugarless. And we want to know, after they've eaten this candy, does their behavior change at all? So in this study, we give them candy, and do they get more hyper or are they not hyper? So let's take a look. There were 65 people that were given sugar candy, and there were 35 children that were given sugarless candy. 53 in total, whether it was sugar candy or sugarless, became more hyper, and 43 children did not. They were not hyper. And when you break it down further, 42 children that were given sugar candy got hyper versus 11. Maybe they felt some kind of placebo effect. Oh, I got candy, regardless of what kind of candy it was or what was in the candy. I got candy, I'm going to be a little more hyper. Okay, so there were 11 of those. That made the total of 53. Now, 23 kids had the sugar candy, and they were perfectly fine. They did not get hyper. They were just kind of their normal selves. And 24 kids got sugarless candy, and they did not get hyper, making a total of 47 there. So if I wanted to pick a random random child and then interview them and their parent. And then at the end of the interview, let them know, here are the results. Did you have the sugar candy or did you have the sugarless candy? And based on your behavior before the candy and what we observed afterwards, did you get hyper or not? Okay. And then ask them some questions about, do you normally get candy at home? Is it more of a treat for a reward, or is it just something that you might be able to get a piece every day? Something that might help. I don't know. Maybe it's a candy factory. They're trying to develop a new candy or something. So what's the probability that I pick someone at random that had sugar? So 65 kids had candy that had sugar in it out of the 100. Okay, now what's the probability that I select someone that did not get hyper? They did not get, they weren't bouncing off the walls. Well, there's 47 of those out of the 100. So what's the probability then that I select someone that had sugar candy and they did not get hyper? So now I've got to look really specifically. Here's the sugar candy column and not hyper. There are 23 of them out of 100. Lastly, what are the chances I pick someone that either had sugar candy or they did not get hyper? So my addition rule says I've got to add the probability of sugar, 65 over 100, plus the probability that they did not get hyper, 47 out of 100. But then subtract the overlap, subtract the ones that had sugar and did not get hyper, because I don't want to count it twice. So I subtract 23 over 100. $65 plus 47 minus 23. This is 89 over 100. A pretty good chance that you're going to select someone that either had sugar or did not get hyper. You can see how these overlapping events and how to calculate certain probabilities, and even just reading data in these tables and drawing conclusions from the data, could be really helpful in the real world. Companies would use this all the time to better, try to better figure out who their base of, who's buying our clothes, who's buying our food, who's doing X, Y, or Z with our products or services. And this is really helpful information that you want to be able to keep with you as you move into the professional world. If you do have questions reading these tables or how to interpret the data within them or finding these probabilities, certainly let me know. I'm always here to help.